Hello all, I am Asghar Rizvi, Assistant Professor, Department of Mechanical Engineering, Khwaja Moinuddin Chishti University, Lucknow. And today I am going to discuss the topic example of shear force and bending moment diagram on a simply supported beam. As you all are aware of that there are many types of beams like simply supported beam, cantilever beam, overhanging beam, prop beam, fixed beam. We will discuss about an example of simply supported beam, that is having only two supports at its free ends. Let us discuss the following example that is here shown in the figure. It is carrying a hinge support at point A and a roller support at point B with a UDL from C to D of 4 kN per meter and a 5 kN point load at point C. So first of all, we will find out the various forces that are acting at various points, and we will draw the free body diagram of this beam. This is the free body diagram of the beam that we have seen in the previous slide. This will be the reaction RA at point A and this will be the reaction RB at point B. We are taking a single reaction in upward direction at point A because there is no horizontal force appearing in this beam. That's why we are only taking it in only y axis. This UDL that is acting between C to D of 4 kN will act at the center of C and D. Since the distance between C and D is 4, so this will act on 2 meter from C and 2 meter from D at the center of C and D. This is the free body diagram to find the reactions at the support. This is the 5 kN point load that is acting at point C, and this is the total reaction 4 into the distance 4. That is the total load of the UDL. This is 16 kN, and this is RB, that is the reaction at point B. To find the reactions, we have to find out through the general conditions of equilibrium. The general condition of equilibrium are sigma fx equals to 0, sigma fy equals to 0, and sigma m equals to 0. We know that all the forces that are acting along x-axis, all the forces that are acting along y-axis, and all the moment that are acting along any point will be equals to 0 if the beam is in equilibrium. So these are the three general conditions of equilibrium. Starting with sigma fi, because there is no force in x-axis, so we are not considering sigma fx. We are directly coming to sigma phi. Sigma phi is 0. RA is going upward and RB is going upward. These are taken as positive and the downward forces are taken as negative. So minus 5, minus 16. Sum of RA and RB is 21 kN. Now moving on to the moment. We are taking moment about point A. When we are taking moment about point A, RA is acting at that point. Since RA is acting at point A, so its perpendicular distance will be 0 and it will have negligible influence on the beam. So RA into 0, 5 into its perpendicular distance is 2. We are taking clockwise moments as positive in this equation. 16 into its perpendicular distance from A is 4, and RB, it is the force in upward direction, it is rotating the beam in anti-clockwise direction, therefore it is having a negative sign. RB into its perpendicular distance is 9. So by these two equations we can find out that RB equals to 8.22 kN and RA is coming 12.78 kN. In some books we can find the shear force sign convention as that when we cut the section towards the left of the section, when the force is upward direction, and towards the right of the section it is downward direction, it is positive. And when the section is cut and the force is downward towards at the left of the section and upward to the right of the section, it is negative. In some books you find the opposite way to solve the question. We can take any one for our question. And for this question we are taking this sign convention, and we will solve it by this only for the shear force calculations. We will find out the shear force at each and every point of the beam. Starting with point A. At point A, only one reaction, that is acting upward to the left of the section, and that thus we will take it as positive, and shear force at point A will be positive of Ra, that is positive of 12.78. Now at point C, we can find that there are only two forces. One Ra in upward direction to the left, and one 5 kilonewton, that is downward to the left. So it will be taken as negative, and this will be Ra will be taken as positive. So shear force at point C will be 7.78 kilonewton. Now we are moving on to the point D. So at point D there will be three forces, one Ra, one 5 kilonewton, and one UDL. So we will find the value of shear force at point D, and it is coming around minus to 8.22 kilonewton. Now at the final point, that is point B, we will analyze all the forces that are acting towards the left of the section, and shear force at point B will be plus Ra minus 5 minus 16 and plus Rb, since Rb is also acting upwards as the sign convention we have taken in this case. The sign convention for bending is as shown in this slide. This is the all the forces that are resulting in upward rotation of the beam, that are taken as positive, and the forces that are rotating the beam in downward direction, those are taken as negative. These are conditions called as sagging and hogging. To find the bending moment, we know that bending moment at the free ends of the beam is always 0. So bending moment at point A and bending moment at point D will be equals to 0, because these are the free end of the beam. So we have to find the bending moment only at 2 points, that is point C and point D. First of all, we will find at point C. Point C, we can see here that Ra is acting on point A, and its perpendicular distance from point C is 2 meters. So bending moment at point C is coming around 25.56 kilonewton meter. And similarly, we can find out at point D. So bending moment at point D is plus 24.66 kilonewton meter. After finding out the shear force and the bending moments at each and every point of the beam, we will finally draw the shear force and bending moment diagram as shown in this slide. This is the shear force diagram that we have calculated at each and every point of the beam. We have calculated at from this point, shear force at point A was 12.78 kilonewton. Since from A to C there is no force acting, so there will be a straight line parallel to x-axis. At point C there is a decrease in shear force by 5 kilonewton, so it will be 7.78 kilonewton. From C to D there is a UDL, uniformly distributed load, therefore it will be an inclined line, and it will come at minus 8.22 kilonewton. And from D to B there is no force acting, so it will go straight, and at point B the shear force will be equals to 0. Talking about the bending moment diagram, at free ends A and B the bending moment is 0 because they are free ends. We have calculated the bending moment at point C and at point D as 25.56 kilonewton and 24.66 kilonewton respectively. We will plot the graph. These will be the inclined lines from A to C and B to D, but from C to D it will be a parabola because UDL is acting between these 2 points. Since you can see that on shear force diagram, between point C and point D, the shear force diagram is cutting the x-axis at point T, at point E. This point will at which the shear force changes its sign from positive to negative or negative to positive, that will be point of maximum bending moment. And at this point, point E, we will find out the value of maximum bending moment acting on the beam. So to find out the maximum bending moment, on the beam at point E, we will first of all analyze the shear force diagram, and we can find that from point C to D, this is the shear force diagram. So to calculate the distance at which the maximum bending moment is occurring, it will be taken as x from C, and the total distance from D to E will be 4 minus x. As we know that from C to D the total distance is 4 meters, and by this formula we can find out the value of x. This will be the distance at which the maximum bending moment will occur, and this distance will be calculated from point C. Moving on to the finding the maximum bending moment, we will draw a section at point E. We will cut the beam, and we will calculate the bending moment as shown here, and we can find out the maximum bending moment acting on the beam. So here we have seen that to find the shear force and bending moment diagram, initially we have to calculate the shear force and bending moment at each points of the beam, and we have to first of all we have to draw a free body diagram of the beam. Thank you.